So I'm Christos Kolias with Orange and the office in San Francisco. So what I'll be covering today is private LTE. And so what is private LTE? Essentially, it's an LTE. It's a private LTE network that it's aimed for the enterprise as a very specific location coverage. So it's meant only for local areas, essentially. It has exclusive users, so it's only for a certain number of users, if you like. And it's optimized and customizable for certain services and applications. And it's readily deployable. And actually, we're going to have a demo later on to show you how easy it is to set up something like that. And it's managed locally, so it does not really interface unless it's needed with the public LTE. So you can see here in the picture, I don't know, we'll have a clicker here, but anyway, so you can see this on the left side, you do like a small cell deployment where you deploy your private LTE, and then you can also have access to the internet if you like to. Say it again? I don't know whether there's any here, but and I'm really. Maybe if I can you see this one here? No, okay, no worries. That's okay. All right, I'll take it. Thank you. That's,
it's not point, it's the top button.
Thank you.
It wasn't showing up on the screen.
Yeah.
Right.
Yeah, all right. Anyway, thank you. Okay. So what really enables private LTE is on the radio access side of things is it's a vRAN. vRAN is for virtualized radio access network, and the vRAN consists of a number of remote radio heads or remote units, as they're called, and also a centralized pool of baseband units. That's where all the processing takes place, and everything is virtualized, so you don't have to run back, and it can even run at a base station. If you like. And how you split the layer 1 to layer 3 functions, this gives different flavors of your vRAN. So if you want to run like layer 1 and layer 2 at the remote head and layer 3 in the back end, it's up to the implementation. And the second component of private LTE is the VEPC, the Virtualized Evolved Packet Core. That's the mobile core for cellular networks, essentially. And the VPC consists of a number of elements to handle the connections and how the user gets attached to the mobile network, making sure that, when you, for instance, if you're using AT&T's network, that you're a subscriber of AT&T's and everything. So it consists of a number of elements, the mobile management entity, the SSS, the PCRF, they always take care of the different mobile functions. And everything is running here as a virtualized component. And then also you have the eNode B, which is essentially the base station for the LTE. Just to give an example, this is like an eNode B that we have for our demo. This is an eNode B from Cavium. You can use other vendors as well. We also have one from Acceleron. So everything is running in virtual machines, or you can run these different components of the virtual packet core in containers if you like. So in terms of the spectrum, right? So what do we operate private LTE? So the private LTE can operate in a licensed spectrum or unlicensed. Now, if it's licensed spectrum, for instance, if it's AT&T in the US, obviously they can deploy that because they have access to the spectrum. But for someone like us that we don't have spectrum in the US, we may have to lease that from an operator. What's really also picking up in terms of speed is CBRS, the Citizens Broadband Radio Services, that operates at 3.5 gigahertz with the band of approximately 150 megahertz. And it's been also finalized now by the FCC. And also you have other unlicensed spectrums like multiplier, which is at the 5 gigahertz. So there are options if you don't want to operate in the licensed space. And the idea here behind private LTE is that you want to boost data speeds over a very short distance. Now, if you're wondering how this is going to work with the SIM card, because you need to have a SIM card that's been provisioned for that private LTE. Today, what happens, like for this particular demo, we have provisioned the SIM cards to work for that particular setup. But if you want to use the same mobile device, the same user equipment for public LTE and private LTE, then you need to have a dual SIM card, or if you are using like the embedded SIM, it's like a digital, essentially, SIM card. It's not a physical SIM card, but it's something embedded in the phone itself. You can do that through remote provisioning. I'm a big believer in eSIM. If you ask me, I think like Apple has that in the iPhone X as a feature, and also it can support very small devices. So another type of device that you can attach to private LTE is also IoT devices. So the kind of use cases that we see emerging, as I said, this is really tailored for the enterprise. It's a perfect fit for campus type of networks, whether it's a hospital, a factory, or a warehouse, and so forth. Multi-tenant buildings, extended public facilities such as airports and ports, and other venues, entertainment or sport venues or shopping centers, remote sites, whether it's oil rigs or mines, and cruise ships, for instance, or airplanes, if you like, autonomous things, drones and robots, and also smart cities and or other type of government type of applications. As I mentioned, it's a really great fit for IoT because of the especially if you can do the eSIM for the remote provisioning, and easy to also implement other type of solutions like third-party solutions, whether it's like AI and machine learning for predictive maintenance, because everything is running in software here, right? So it's easy to essentially, if you have the right APIs, to add that to your setup. So network slicing and private LTE. So if you can add slicing, and I'm assuming that most of you are familiar with the concept of slicing or network slicing. So essentially, in network slicing, you use one physical infrastructure, and you just create virtual networks across that physical infrastructure that essentially you can manage separately. And this is like isolated instances of your network. And when it comes to private LTE, there's like two types of slicing. There's the slicing on the RAN side, on a radio access network, which is like partitioning your radio resources. And there's slicing on the mobile core side. That's where essentially you will segregate your mobile traffic. And here, what I'm showing here is, again, how you can slice your infrastructure across your network from the radio access side here all the way back to the core. What's really has been attractive to us in terms of the slicing, and we've been partnering with Netsia, and Oz will be giving a talk later on, is the idea that you can do slicing in a very dynamic way. That's what we see as a game changer in this space, that I can allocate slices on the fly if I have to. I can my bandwidth can be elastic, so I can assign different capacities on different slices, and I can do selection again in a very dynamic way. I think in theory you can do an infinite number of slices with dynamic slicing, but for practical purposes it wouldn't make sense if you have like hundreds % of your bandwidth to do more than, let's say, 100 slices, right? If you do 100 slices, the maximum you can have per slice is 1% of your total bandwidth. So in actual practical terms, I don't think you should do more than 10 or 20 slices, right? But again, I don't think there's any limit in theory Each slice can have its own policies as far as security and also its own resource in terms of storage and processing, and also its own VNF. So you can run like firewall on one slice, you can be a different firewall on a different slice, or load balancer, and so forth. You can have context-aware slices. So for instance, you can assign a slice for voice traffic, for instance, or for video traffic, or if you're using Instagram or Facebook, you can have all your traffic running on that slice. This is something that's going to be up to the customer to decide how they want to do that. And another example here is that you can have different slices, for instance, for different IoT applications, and that would be very applicable for the healthcare type of use case. Maybe you know that network slicing is already an integral part of 5G. Okay, I think I'm going to skip the details about round slicing. Maybe Oz can cover that in more detail. But essentially, the way you do that is you have a number of resource blocks that are like in frequency and in time, and you just, the algorithm behind that is how you can allocate, these blocks to the different slices. What's really, of course, interesting and what's really desirable is the end-to-end slicing. So you have, as I mentioned, you have the run slicing and you have the core slicing. So the thing is that how you can stitch together those two types of slicing to create an end-to-end slice that can run all over back to your core. So for instance, if you are connecting to a public LTE, maybe you want to have a slice that extends to that public LTE. So for instance, to give an example, Uber, right? Uber may deploy a private LTE in the city of San Francisco, but maybe they want to extend beyond the city of San Francisco. So they're running a private LTE within San Francisco, but then they want to maybe utilize the public LTE to go outside. And the other thing is that if you take, again, Uber as an example here, if they have a private LTE in San Francisco and there's another one in LA, obviously they want to stitch those two slices together to create a unified slice for operational purposes. Another interesting thing might be one day to extend the slice all the way to your mobile phone. So for instance, that will allow you, again, voice calls to go on one slice and other types of traffic on a different slice. You can have one slice for your personal stuff, and you can have another slice for your business, right? So you start essentially virtualizing the phone itself. 5G is coming up. As you know, there's a lot of things going on in this space. And we expect multitude of performance improvements. In terms of connectivity, if you look at a small cell aggregate connectivity, can be even 10 to 20 gigabits per second. If you like, that's like 1,000 times improvement from what we have today. It can support, in terms of uplink, up to 100 megabits per second and downlink 50 megabits per second per device. It's going to be much, much denser than today's 4G cells, so we'll be able to support more devices per square mile, if you like. And that includes also the IoT devices, and it's supposed to be also a huge battery saver. So the 5G is going to also extend the spectrum to the millimeter wave range, which is between 30 and 300 gigahertz. Using technologies such as massive MIMO for beamforming. And 5G also relies heavily on SD and NFV as enabling technologies. The two deployment modes today, one is non-standalone, the NSA. That's where it utilizes the control plane of the existing LTE that's existing in 4G. And the standalone, which is the next step, is to essentially have a pure 5G network in terms of the signaling and the data traffic. So today, just to give you an idea, they're just deploying the NSA. So they trying to, so the radio access network is a 5G, but the mobile core is still using the old 4G technology. So in terms of implementation efforts, what we happening today is that a lot of talk about fixed wireless broadband. Essentially, you have like an antenna, and you're able to use a 5G for that antenna to send traffic to hotspots and essentially mobile CPs in your home. By the way, I was reading something yesterday that the Verizon has been trying to do that in Sacramento, and the take-up so far has been very disappointing. I think this is going to work best for places that are really hard to reach in terms of internet. So like rural places or places that it's going to be super expensive to run fiber. If you already have DSL or some other type of broadband technology in your house today, I don't think you're going to opt for 5G, right? So I don't know whether that explains what's happening in Sacramento and Verizon, but that was like in one of the articles that I read, came across actually yesterday. So that's happening today because it's available today. We don't have 5G handsets today. They are coming out by June, I believe. There may be some experimental models. So they're looking into how you can deploy 5G as a fixed wireless broadband today. So again, the early trials happening around the world, in the US, of course, and other places in Asia and in Europe as well. And we expect widespread deployment by the end of 2020. This is actually what I'm showing here is our research labs in Paris. So you can see the 4G antenna here, and next to that we have a 5G. You can see that it's almost half the size. So it's smaller in terms of footprint, but you're going to need more of these because it's like more small cells, right? So that's going to present its own challenges. In terms of deploying 5G, it's going to be more cells. So essentially, it's going to be more expensive. And actually, I worked on an article that's published on Pipeline that we go through some of the challenges on 5G. So when it comes to 5G and the edge, private LTE and 5G and the edge. So first of all, private LTE applies to 4G as it is today. With 5G coming up, this is going to be called private mobile networks, and we see some traction today happening in private LTE. As I said, there's like certain use cases that are very, very attractive. Now with 5G, we're going to have more spectrum, so there are going to be ample more opportunities there. So when it comes to the edge, and this is something I think I borrow from Intel. So the edge, people are really questioning what is the edge. I mean, to me, it doesn't really matter what the edge is, right? The edge is what you think it is in your case. If you're a factory, then your plant essentially is the edge, right? If you're like a telco, maybe my central office or the base station is the edge. So it doesn't really matter. But we think that private LTE and the edge, there's definitely a synergy there, and private LTE can support other edge applications. So we're looking, for instance, to run an edge application that we have in mind on our private LTE testbed. And the idea behind that is because you're going to leverage the virtualized environment. So for instance, in this setup that we have, we're using like an Intel NUC that's running VMs or containers. So on that same hardware, you can run other software solutions like firewalls and load balancers and so forth. And the interesting idea here, the autonomous networks here is that there was an article a few weeks ago, I believe, where Nokia and BMW were in a partnership with China Unicom to install a private LTE at a factory in China. So obviously this is something that's happening today. So what are the business implications, right? So the fact that you have this kind of softwareization happening has made private LTE very, very low cost alternative, and which is very attractive as a solution. In fact, the software costs more than the hardware. But hopefully Netsia can help us, bring down the cost, right? Or, yeah. Anyway, it can enable very high capacity, low delay applications such as AR and VR, and this we're planning to do something later on. Maybe robotics in the future and imaging. It provides universal connectivity because you need one network to provide coverage. You can go for a radius of, even a couple of miles if you want. Depends on how much power you want to emit. It's very scalable, so we don't have any issue of scaling up if we want. Has embedded security because of things like slicing, and you can run also other virtualized security solutions on top of that. It's hardware agnostic, as I said, it doesn't matter whether you're using a Cavium Inode B. By the way, the Cavium Inode B is not commercial available. We have another one from Accelerant, which is for commercial purposes. The interesting thing about private LTE is that it provides a unified management of the radio nodes, right? So you can have different Inode Bs, different radio stations from different vendors, but it's one platform that you need to manage all these different radio stations. It's very easy and fast to install and essentially deploy. And again, it's one wireless network that you need to manage. I think that's the value proposition for private LTE. I think it's also going to be proven to be, as a solution, more attractive than Wi-Fi. Again, you have one single base station that can provide coverage, as opposed to having multiple access points. For instance, if you have like a port, like the Port of Los Angeles is deploying private LTE today, and the idea there is that they need just one base station to, for coverage, instead of like having to install and deploy a number of different access points. It can provide quality of service support that does not exist today in Wi-Fi. You can use slicing to prioritize traffic. Easy support for public safety applications. And also you can use calendaring and scheduling, right? So if you want to use particular slice for certain times of the day because for whatever reason, you can do that. Again, it provides a single pane of management and visibility, has enhanced security as I mentioned before. You can use slicing to create network IDs. So if you're missing your network IDs on a Wi-Fi network, you can use the same concept of slicing if you like. But again, it provides one single management point. It can provide support for voice over LTE, and also it eliminates the provision complexity that comes with Wi-Fi, and that's a really great alternative. Alternative for IoT. Okay, so this is the setup. I'm not going to go through the demo right now. It's going to be at the end of Oz is going to be next to talk about Netsia and its products. What we have set up here, it's a private LTE network, and it consists of an Intel NUC that's sitting on that table. There's an Inode B from Cavium, the small white box there. That's your radio. Essentially, and then there's a software that runs on the VPC that's from Christos, and we plan to also install the open source version that Intel and Sprint has been working on, and also the Netsia's run slicing software, which is called Program. So you can see the setup there, and this is the same setup here. And the use case that we're using for this particular testbed is the hospital use case, where we have a number of slices. So you can think the use case where staff has its own slice, the patients have their own slice, the visitors that come into the hospital have their own slice, and staff gets the highest priority. And let's say there's an earthquake happening, and you want to assign more bandwidth for the staff because there's an emergency. You can do that with the click of a button, right? Or with the ease of using an iPad. I think I remember one of the first demos I saw from Netsia back at MWC is that you can actually use your iPad to essentially change how bandwidth is assigned to different slices. Okay, and this is the actual testbed that we have back in the office in San Francisco. All right, I'm going to hand it over to Oz Oktay from Netsia. And I believe Oz has animation. We couldn't get the full demo working in terms of how we can change the slice and everything. But we're going to do another version of it. But I believe you have some animation that you may want to show. Fantastic.
Okay, so today I'm going to talk about what we are recently doing on the virtualization of the telco edge. So this presentation will include what we are doing on the radio side as well as on the fiber side. So This is current radio network, right? The 4G, 3G, 4G network. So we have antennas, RRUs on the left-hand side, and then BBUs. BBUs can be on the edge or on the core, so this is the existing architecture. What we are currently doing is creating a split between the core components and the components closer to the edge. They are called distributed components on the edge, and then core components are called CU. This is the 3GPP, standard 3GPP architecture for the 5G, actually. So we are implementing it, and at the same time, on the core side, we are virtualizing the components. This is the standard for most of the other vendors. But actually, there is a problem here. So we have the core components and the distributed components. How are we going to connect them? We have to find a way, a feasible way, so that these deployments would be feasible. Actually, the reason that 3G and the 4G small cells didn't deploy it widely was the transport problem. So we couldn't find a feasible transport in order to deploy these small cells. So we have the same problem here. So we are trying to find a solution to that. And the one solution we are focused recently is the PON networks, passive optical network. This also came from our partner operators because they have widespread PON network deployment, and they are underutilized, and they want to use it for other purposes. So we decided to use it for the transport between the distributed and the core components. Of course, we are also adding our innovative slicing solution on top of that. So the slices are available on both the DU and the CU side. Christos talked about the slicing a lot, so I don't want to go into details on what we are doing on the slicing. We are also following the ORAN architecture in order, so the ORAN defines very well interfaces between the components, and it also defines an external component called RIC, a centralized intelligent component. So one of the reasons that they are offering this is to reduce the intelligence on the DU and the CU components, and then gathering them in a centralized place. So we are following that architecture, and then we created our RIC, and actually we put our slice management logic into the RIC as well. So since that we have now both the optical network and the cellular network under our control, we could have some use cases. So I'm going to show you one of the use cases we created. This may be called bonding on the edge. Okay, I will speed up. So as you can see on the residential gateway on the left, there are two data paths. One is connected over the optical network. The other one is connected over the cellular network. So that data can go from either of these paths, but we have to bring them together, right? So they are usually brought them together in the core network, but we put our aggregation server on the edge, so that these data paths can be brought them together on the edge, and this gives us a local breakout capability even for the bonding case. So we implemented that. Is an example use case for fixed mobile convergence. So there are other use cases we can talk about later. Now, of course, by the way, we are extending or slicing ideas into the PON network as well. So that on the transport level and also on the user plane level for the residential access, we can create slices. And all these slices and on both PON and for the cellular can be controlled with this single edge controller. We call it intelligent edge controller, which can also control these services and applications. But of course, we also need a centralized orchestrator which can manage the network end to end. So here we started integrating with an ONAP, a centralized orchestrator, as a POC. So we already created a closed loop control over slice reconfiguration. But then later our customers wanted us to integrate with OSM-based Unica orchestrator. Now we are more deeply integrated with OSM-based orchestrator, and we are still working on that. And of course, there could be existing OSS BSS systems. We are also integrating for the legacy OSS BSS systems for some of our customers. So that is what we are currently focused on very recently. As I said, we are following ORAN architecture, and we are active in the ORAN consortium. ORAN, the architecture and working groups. We are participating some of them. Let me show. And we are especially active on the RIC-related working groups. Actually, for the working group 2, we are the editor for the use cases and the interfaces. So that's all I want to talk about. Because of these projects, we are involved with multiple operators, including Orange, and then we actually started developing some projects together with them based on their own requirements. Our engagement with Orange Silicon Valley was providing them a test platform which they can utilize to run some of their ideas. One of the idea was, of course, these private LTE healthcare, and there was an IoT idea that we also implemented on that platform. That's it, what I'm going to talk about. But before I finish, if I have time, I just want to show an animation which explains what that platform can do. Let me run that. Okay, so this is an hospital environment where there are different type of users. For each user type, we are creating profiles. So there are doctors, of course, patients, and then visitors, and also IoT devices at the hospital that are communicating over the cellular network or private LTE network. So we have a profile for visitors, critical IoT. Critical IoT means the medical equipment, right, communicating over the cellular network. There we can also create a slice for non-critical IoT, like air conditioning controls. So all these profiles are getting different type of service on the same small cell or the macro cell installed on the hospital campus. And that, of course, a device is connected to the central core over the PON network. So as you can see, we have different capacities. You cannot see well, but anyway, so we are allocating different capacities for different type of users. For example, 40% of the capacity goes to the staff, and only 5% is allocated for the non-critical. Okay, I'm almost done. So let me speed up. Okay. So as we talked before, an earthquake happens and it automatically triggers the emergency mode at the hospital management system. That also triggers some changes on the slice allocations, and we provide more capacity to doctors. So that was the animation.
So I'm going to make a call. Again, this is private LTE, right? So that's whether it's the public internet. So actually, we couldn't get the internet working, so cannot be better than that. And let me call William. Hi, can you hear me? Yeah. Okay. Yeah, actually, you don't have microphone, so I'm just using the a web application running actually here to call. So let's pretend I'm doctor and William is a patient. I'm able to call him. So what we would like to show, of course, is that like the case that was demonstrated, how you can change actually the bandwidth allocated for different slices. Unfortunately, we couldn't get the internet working here, so I'm not able to do that. But at the end of the meetup today, you're more than welcome to come and see that this is the setup. Whatever you see on this table is what really enables private LTE. I put this, I got this in a box, and that's why we call it private LTE in a box. It's very easy to set it up, it doesn't take too much effort. And that's it. Do we have time for questions, or you want to do questions, or? And I know whether the people on the internet can hear us because the